Well, I guess after that I should just go sit down. Tom has been too kind to me, but I want to thank Larry, I want to thank Tom and all of you here at ONR who are responsible for me standing up here right now to talk to you. By the way, what I have to say, I want everybody to sit back and relax. There are no equations in this presentation. What is in this presentation? Well, we have an airplane up on the screen. And I'm going to do something that I only do when I talk about this subject. I'm going to read to you for a short while from a book. And I'm going to read to you the circumstances surrounding the flight of the Bell X-1. So just sort of bear with me here for a minute. The morning of Tuesday, October 14th, 1947, dawned bright and beautiful over Muroc Dry Lake, a large expanse of flat, hard surface in the Mojave Desert in California. At 6 a.m., teams of engineers and technicians at the Muroc Army Airfield began to prepare a small, rocket-powered airplane for flight. Painted orange, well, not in that photograph. You have to go to the Air and Space Museum today in the Milestones of Flight Gallery to see the one that's painted orange, the X-1. And resembling a 50 caliber machine gun bullet. Every once in a while I'm going to wander, since I sort of have a nice, technically oriented audience. The shape of the fuselage of the Bell X-1 is the shape of a 50 caliber machine gun bullet. And why is that? If my wife were here, she'd say, already too much information. Pardon me, but I have to tell you why that's shaped like a 50 caliber machine gun bullet. When the Bell engineers in 1944 started the design of the Bell X-1, there was virtually no information on transonic, or especially transonic airplane design. They knew that at the Aberdeen Proving Ground in Maryland, the Army had lots of information and experience with projectiles, including 50 caliber machine gun bullets. They went to Aberdeen, they picked up data on such a shape, aerodynamic shape, and presto, the Bell X-1 fuselage is shaped like a 50 caliber machine gun bullet. Well, that was a timeout. Time is back in again here. This Bell X-1 was carefully installed in the bomb bay of a 4-engine B-29 bomber of World War II vintage. At 10 a.m., the B-29 took off and climbed to an altitude of 20,000 feet. As it rose past 5,000 feet, Captain Chuck Yeager, a veteran P-51 pilot from the European theater during World War II, struggled into the cockpit of the X-1. Yeager was in pain from 2 broken ribs incurred during a horseback accident the previous weekend, but not wishing to disrupt the events of the day, he informed no one except his close friend, Captain Jack Ridley, who was helping him to squeeze into the X-1 cockpit. At 10:26 a.m., at a speed of 250 miles an hour, the brightly painted X-1 dropped free from the B-29. Yeager fired his reaction motor's rocket engine, and powered by 6,000 pounds of thrust, the sleek airplane accelerated and climbed rapidly, trailing an exhaust jet of shock diamonds, which you can see there nicely in the photograph. From 4 convergent-divergent rocket nozzles of the engine, the X-1 was soon flying faster than Mach 0.85. The speed beyond which there were no wind tunnel data in 1947, and beyond which no one knew what problems might be encountered in transonic flight. Entering that unknown realm, Yeager momentarily shut down 2 of the 4 rocket chambers, carefully tested the controls of the X-1 as the Mach meter in the cockpit registered 0.95 and still increasing. Small invisible shock waves were dancing back and forth over the top surface of the wings. At an altitude of 40,000 feet, the X-1 began to level off, and Yeager fired 1 of 2 shutdown rocket chambers. The Mach meter moved smoothly through 0.98 and 0.99 to reach 1.02. There the meter hesitated and then jumped to 1.06. A stronger bow shock wave was formed in the air ahead of the needle nose of the X-1 as Jaeger reached a velocity of 700 miles per hour, Mach 1.06, at 43,000 feet. The flight was smooth. There was no violent buffeting of the airplane and no loss of control, as had been feared by some engineers. At that moment, Jaeger became the first pilot to fly faster than the speed of sound, and the small streamlined Bell X-1 became the first supersonic airplane in the history of flight. Now, I'm going to go one more little paragraph later. As the sonic boom of the X-1 propagated across the California desert, that flight became the most significant milestone in human flight since the Wright brothers. First flight at Kill Devil Hills 44 years earlier. Just 44 years separated the first supersonic flight and the first flight of a successful powered airplane. 44 years. Anyway, that flight was equally significant in the history of scientific accomplishments, the Bell X-1, for it was one of the high points in 260 years of research into the mysteries of high-speed gas dynamics and aerodynamics. In particular, it was the climax of 23 years of outstanding research in high-speed aerodynamics carried out by the NACA, research that is one of the most important stories in the history of aeronautical engineering. And that's the story I want to share with you today. The story of how we got the intellectual background, the intellectual knowledge to allow this flight. Now, that's the title of the talk. Okay. We're sort of frozen there for a minute. Help? No. Oh, there we go. Sorry about that. Prehistory. 3 things I want to share with you. A little bit of prehistory, explaining the compressibility problem, which had to be dealt with, and learning how to deal with it, those 3 things. And while that's on the screen, first, a little bit of prehistory. This airplane broke the speed of sound. What about the speed of sound? For those of you who play golf, you know the following rule of thumb, that if you're out on the golf course and there's a thunderstorm coming up in the distance, and you see a flash of lightning out there, and you start counting 1, 2, 3, 4, 5. For every count of 5, that lightning was 1 mile away. And so clearly, sound travels at some finite speed. Light travels 186,000 miles per second, almost infinitely fast. Sound travels at a speed at standard sea level of about 1,117 feet per second. So clearly, sound travels at some speed through the atmosphere, the speed of sound. Now, the aspects of how do you find out what the speed of sound is? 260 years, well, put it this way, in 1687, in Newton's Principia, Isaac Newton derived for the first time an expression for the speed of sound, to calculate the speed of sound. Prior to that, the speed of sound had been measured in somewhat the same way that this golfer's rule of thumb that I mentioned to you. Back in the early 1600s, way off in the distance, a cannon was put on a hill. People were standing way over here on another hill. Cannon was fired, and the people over here started timing the amount of time it took them from the time they saw the muzzle flash to the time they heard the boom from the cannon. And in that way, first measurements of the speed of sound were made. This is in the early 1600s. And it was measured at about 1,140 feet per second. That was pretty accurate. again, the standard sea level speed of sound is 1,117 feet per second. So here we have, towards the end of the 1600s, the end of the 17th century, physical knowledge of what the value of the speed of sound is in air, and we have Newton making a calculation of the speed of sound in air. Now, problem was that Newton assumed that the thermodynamic process through a sound wave was isothermal, constant temperature. And we know today that's not the case. It was just an error in assumptions. Newton calculated 970 feet per second for the speed of sound. It was about 15% lower than the observed value experimentally in this sort of experiment from looking at one hill to propagating sound to another hill. But it's interesting. Newton did something that most scientists did in those, and still do today. He rationalized, well, there's humidity in there, there are dust particles in the air, there are all kinds of things going on in real life that would make his calculation different than the measured value. So he felt comfortable being within 15% of the measured value. It wasn't until the early 1800s, about 1810, that Laplace, the great mathematician and physicist in France, Laplace made the correct assumption that the thermodynamic process through a sound wave was adiabatic. Today we'd say isentropic. And with that, Laplace came up with the correct formula for correctly calculating the speed of sound. And so here we have, at the time of Napoleon, knowledge of what was the speed of sound and how to calculate it. And every once in a while, in my classes at the University of Maryland, I was teaching this, I used to think, oh, this is pretty interesting, fairly new information. It's not new information, because 260 years before this flight that I showed, the Bell X-1 flight, knowledge about the speed of sound was known. Okay, so that's speed of sound. Well, we talked shock waves. I read to you about shock waves dancing over the top surface of the wing of the X-1, shock waves. Well, existence of shock waves were known, that was known in the by the middle of the 19th century. Even maybe earlier than that, it was brought up because every once in a while in coal mines, there would be an explosion and there'd be this blast wave that would come out of the entrance of the mine. And so people recognized there was something that really shocked you if you were standing out there in it, and that the existence of shock waves was postulated. And then along comes a professor at the University of Glasgow, Rankine, who for the first time, this is 1874, I guess, 1874, makes the first proper analytical calculation, comes up with the first equations to allow calculation of properties behind a shock wave. This is 1874. And about 16 years later, Hugonio in France, without knowledge of Rankine's work, came up with the same set of equations. We call these equations today the Rankine-Hugonio equations. For any of you who have studied compressible flow, you have studied the Rankine-Hugonio equations, the equations for changes across a normal shock. And so these equations for calculating properties across shock waves, they were known before the turn of the 20th century. And in addition, what you're looking at there is a photograph, a Schlieren photograph of the first time that human beings saw by the naked eye shock waves. This was an experiment carried out by Ernst Mach, 1887. This is basically like a .22 caliber bullet that he fired down a range, and he had an optical system, these vertical lines there are part of his tripwire mechanism for taking the picture. And there's a picture of shock waves. Here's our supersonic projectile. Here's the shock wave off of the nose of the bullet. First time in history that you actually saw a shock wave. Really historic. 1887. Ernst Mach. Ernst Mach was, in many respects, a universal man. Some people felt he knew everything about everything. And by the way, Mach did a lot of work in high-speed flows, but he never coined the word Mach number. The word Mach number, the term Mach number, was coined much later after Mach's death by Jakob Ackeret in 1928 in a speech that Ackeret gave in Germany, in which he used the term Mach number. Mach number. Let me elaborate on that. It took a while for the Mach number to become adopted in the Western literature, in the English, in England and in the US. Mach number. I defy you to pick up some English literature during the early 1930s and find the word Mach number used. The NACA always talked about the speed ratio, the ratio of velocity divided by the speed of sound, which is Mach number. But in those earlier NACA reports, it was always speed ratio, not Mach number. It wasn't until 1938 that I found the word Mach number used in an NACA report. So, unlike our world today where information travels at the speed of electrons and the speed of light, basically, it took a while for scientific information to be disseminated around the world in those days. But anyway, this was important. Now, before I go any further, since being here at the Office of Naval Research, I'd like to draw a contrast between what I've just told you and what I'm going to talk about next. And that contrast has to do with the difference between science and engineering. Now, we all kind of have our ideas, sure, science, engineering sort of applied science and so forth, but not so really. There is a very well-known professor, retired professor at Stanford, Walter Vincenti, who has become, in the last 30 years, a major expert and a major thinker in the history of technology, and he wrote a book. This book is called What Engineers Know and How They Know It, published by Johns Hopkins University Press. It's about 1996 when he did this. And Vincenti, in that book, makes a clear distinction between science and engineering. Think about this. Science is the endeavor or the efforts to study and understand phenomena in the natural world just for the purpose of understanding them. And then this gets published in the literature, and that's what scientists do. Engineers, on the other hand, engineering in Vincenti's terminology is an entirely different bulk of knowledge. Engineering is a different bulk of knowledge than science. It is an established bulk of knowledge that engineers have developed over the years about how to do things, how to design artifacts, and things that work. Even though some engineering approaches, some engineering theories are diametrically opposed to what goes on in physical science. One example that I always point out, I have worked in the field of hypersonic aerodynamics. You want to calculate the pressure distribution over the blunt nose of a hypersonic vehicle. You can use something called the Newtonian sine squared law. And it does a pretty good job of giving you the pressure distribution around a blunt nose vehicle, Mach 10, Mach 20, Mach 30. Newtonian pressure distribution. Even Newton himself said that this does not hold any water in physics. is totally wrong. But we still use it today for engineering calculations of pressure distributions over hypersonic vehicles. So that's an example. So here's Vincenti saying science, bulk of knowledge, developed, published, put in the library. Engineering, a totally separate bulk of knowledge for the purpose of designing an artifact. Now, especially after World War II, and this is where O&R came into play, there came what I would consider, what a lot of people would consider to be engineering science. Now, what is engineering? Oh, by the way, everything I've talked to you about so far is science. The measurement of the speed of sound. That was done, put in the library. Calculations of speed of sound. That was done, put in the library. This photograph, this observation of shock waves on a supersonic projectile. Done, put in the library. Scientific knowledge, that's what these people were after. Now, what I'm going to be showing you after this is what I would call engineering science, combination of the two. What is engineering science? Engineering science is that intellectual endeavor for the acquisition of new knowledge for the purpose of designing artifacts, not just to go into the library, but for the purpose of designing artifacts. And so everything else I'm going to mention this morning really falls in the category of engineering science. Okay. First of all, what you're looking at there is some experimental data on the drag experienced by a projectile flying through the air. This is carried out by Bensberg and Kranz, two people who were concerned with artillery shells in Germany in 1910. And they measured what, this graph is the, oops, that's not what I wanted to do. This graph shows the variation of drag coefficient versus velocity. Now, you can't see the numbers on this graph. It's a terrible graph. You never present this in a group like this. But so I just point out, I mean, this is their graph. And what is going on here, way down here is something called basically a drag coefficient. And it's showing that this is drag coefficient versus velocity of the projectile. So as the velocity is going up, suddenly this drag coefficient is going up radically. It peaks out at something like about on the order of 350 meters per second. That's the velocity here. And the standard speed of sound is about 340 meters per second. So right about the speed of sound and slightly below, you have this tremendous increase in drag on the projectile. And then the drag coefficient becomes actually smaller as you go to supersonic speeds. That's well known today. That's the drag coefficient. That doesn't mean the drag goes down. If it did, that'd be great. You know, every time an airplane exceeds the speed of sound, then you just sort of cruise over the downhill and fly into oblivion. It's the drag coefficient. And for those of you who know aerodynamics, you take the drag coefficient, you have to multiply it by the square of the velocity and the density of the air and 1/2 and so forth. But 1910, what this is saying, in 1910, it was known that when projectiles crept up to the speed of sound and beyond the speed of sound, there's this big increase in drag. That was even noted there back in 1756. Benjamin Robbins in England had developed a way, he was a ballistician, and he had developed a ballistic pendulum that would allow him to measure the drag versus velocity of projectiles. And as he got up close to a number that he recognized as being close to the speed of sound, he observed these drag of the projectiles increasing faster than the square of the velocity. And that meant hey, something different is happening when you get up close to the speed of sound. And that's drag. So that it was known at the turn of the 20th century that drag increased dramatically as you snuck up, as you approached the speed of sound. Now, during World War I, we flew, airplanes were flying. World War I was a development period for aircraft. And there was an interest now, not just in drag, but an interest in lift, measuring lift as a function of velocity, lift on a wing, lift on an airfoil as a function of velocity. What happens to the lift as the velocity increases? We just looked at what happened to the drag as the velocity increased. It goes like that. What happens to the lift? Two guys at McCook Field. Larry has a relative who worked at McCook Field. I was impressed by that. Frank Caldwell and Elisha Fields. They were at McCook Field, Dayton, Ohio. 1918, they built a wind tunnel and carried out tests in that wind tunnel at velocities from, whoops, that keeps wanting to go that way. From velocities of from 25 to 465 miles per hour. This wind tunnel at McCook Field could achieve 465 miles an hour. I mean, that's phenomenal. Here we are in 1918. We have airplanes like the famous airplanes like the French Spad, the Sopwith Camel, so forth. These airplanes flew at 125, 130 miles an hour. Here's a wind tunnel that has been developed that could reach 465 miles an hour. Now, is this because that the Army at McCook Field at that time had some people who could look well into the future and would know that someday, 15 or so years from then, that airplanes might be flying at those velocities? Not really. There was, when you look at World War I airplanes, there was a part of the World War I airplanes that did reach the speed of sound, or up to the speed of sound. It was the propeller. If you think about if you imagine that you're a propeller, and here the propeller is going around and around, you go out to the tip of the propeller, you're moving at a very high velocity, rotational velocity out there. It's like the old vinyl disc on a turntable. In the center, the velocity is not very large, but out on the rim of the record, the thing is going around like mad. Same thing with the tip of a propeller. And so even though the airplane may be flying at 125 miles an hour, if you combine the rotational speed, the velocity due to the rotation of the propeller out at the tip with the forward speed, velocities on the order of speed of sound had actually been realized. These two guys, Caldwell and Files, worked in the propeller section at McCook Field, and they were highly interested in the characteristics of what happens to the airfoil sections of propeller blades out at the tip when speeds near the speed of sound were reached. They tested airfoils 8% to 20% thickness. And they got something that looked like this. This is another graph I have to go over here and kind of explain for a minute. They are now interested in lift, not necessarily drag. But here's now suddenly, for the first time, these were the first experiments in which a focus was put on the lift for airfoils at high speeds. And Caldwell and Files discovered, this is lift coefficient versus velocity again in their high-speed tunnel. Remember, it could get up to 450 miles an hour. And it showed, this is low Reynolds number stuff down here, forget that, but it showed a lift coefficient relatively constant with velocity. Now we know today that the compressibility effects slightly increase the lift coefficient, but in those days they didn't have a very accurate way of reducing the data. But the big thing is, look, what happens to the lift suddenly when you get out here to high velocities? The lift falls off the cliff. That's really dramatic. And they knew at the same time that the drag increases out of sight. And here, suddenly, the first knowledge that the lift was falling off the cliff. This is 1918. Now, nobody had a clue as to why this was happening. Okay. That work at McCook Field was actually sponsored by the NACA, the fledgling NACA that had been created in 1916. Here in 1918, they're carrying out, they sponsored this work at McCook Field. And they also sponsored some work at the National Bureau of Standards. Lyman Briggs and Hugh Dryden. The name Hugh Dryden, I'm sure, is familiar to many of you, who later on became Director of Research for NASA. And as a matter of fact, Hugh Dryden, it's interesting. Hugh Dryden graduated from the Johns Hopkins University in 1921 with a PhD in physics. And what was his PhD dissertation topic? High-speed compressibility problems over wings, over airfoils. So this was his bailiwick. And at the National Bureau of Standards, in a fairly large 12-inch wind tunnel that was jury-rigged up at the General Electric facility in Lynn, Massachusetts, these two guys carried out tests, wind tunnel tests, near the speed of sound. And they observed, just like, I'm going to go back, this velocity at which the lift falls off the cliff. Caldwell and Fales called the velocity where that started to happen the critical velocity. That was the beginning of the term that we use today all the time called critical Mach number. But that was the critical velocity. And these guys in this wind tunnel discovered such, they kind of verified what was discovered at McCook Field. Lift decreased dramatically as you reached or went beyond this critical speeds. Drag increased dramatically. Center of pressure shifts rearward, that was a big problem. And the critical speed at which these things occur actually decreases as the angle of attack is increased and the airfoil thickness is increased. So they were, Briggs and Dryden were verifying the phenomena observed at McCook Field. But nobody knew what was causing the problem. Why? Let's look a little further. The same two people, a few years later, 1926, still at NBS and still sponsored by the NACA, carried out additional tests in a much smaller high-speed wind tunnel. This was now at the Edgewood Arsenal in Maryland. A little tiny wind tunnel that had about an inch and a half test section. They put little tiny wing models in there and punched some pressure taps. In each model, they punched 2 pressure taps. And they made 7 models with the pressure taps at different locations. And with this, they were able to obtain a pressure distribution over the airfoil at speeds near the speed of sound, beyond this critical speed. And what did they see? They saw a pressure distribution, which if you, I'm going to draw a picture in the air. Here's the airfoil, here's the flow coming in. The pressure at the leading edge is stagnation pressure. Pressure goes down as it expands over the top surface. And then suddenly there's a little increase in pressure and a plateau. For the downstream, a plateau. Now, it was known at this time in 1926 that an airplane wing, when an airplane wing stalls, you're flying along, you increase the angle of attack and you continue to increase the angle of attack, and all of a sudden stall occurs, the lift drops, the airplane drops out of the air. And pressure distributions had been measured on wings of airplanes that were in a stall. And they discovered with these pressure distributions over the top surface of wings in a stall that it had this pressure plateau over a large portion of the wing. And so Briggs and Dryden concluded that these pressure distributions they observed must have indicated separated flow. Somehow the flow was separating, even though these airfoils were at 0 degrees angle of attack. They weren't up at high angle attack. They were 0 degrees angle attack, and all of a sudden it looked like the pressure distribution was synonymous to that you would have for a wing and stall. So they concluded the flow must be separating on the top surface of the airfoil. And they further carried out oil flow experiments. They smeared some oil on the top surface of the little wing models, and they observed the telltale accumulation of the oil on the top surface of the wing, showing flow separation. So here it is in 1926, the intellectual knowledge of what was happening on a wing or an airfoil as you approach the speed of sound was beginning to develop. It was being called, these bad things, lift dropping off the cliff, the drag going out of sight, somehow were associated with flow field separation. Same sort of thing that happened when the wing stalled at high angle attack. But again, this was at 0 angle attack. So still, the question is, what was going on? They had no clue. Okay, now, 1928, this man walks through the gates of the NASA, the NACA Langley Memorial Laboratory. His name is John Stack. He had just graduated with an aeronautical engineering degree from MIT, and he was put in charge and working with a high-speed wind tunnel, quote unquote, a high-speed wind tunnel at Langley. It was being developed. I'll go over here and point some more. Very interesting thing. At Langley, there was something called a variable density wind tunnel, a wind tunnel which was pressurized to 20 atmospheres so that airfoil experiments could be carried out at high Reynolds numbers. The variable density wind tunnel was built in the early 20s, famous. It put the NACA on the worldwide map, this variable density tunnel. And essentially, it was a wind tunnel inside a pressure tank. The pressure tank was pressurized to 20 atmospheres. Now, when a test was finished in this variable density tunnel, this 20 atmospheres had to be drained out, had to be exhausted the atmosphere. Well, John Stack and his colleagues theorized, well, my goodness, why don't we use this exhaust from the variable density wind tunnel? Oops, keeps wanting to do that. This exhaust up here is acting like an ejector. And here's flow in a room down below the nozzle. Flow is being sucked into the nozzle by this high-speed ejection of air from the variable density tunnel. Here's a test section. There's an airfoil mounted in that test section. And speeds near the speed of sound could be achieved in this facility. This is the NACA high-speed wind tunnel. And John Stack measured, for the first time, really, the first truly definitive airfoil data at high speeds. This is a Clark-Y airfoil, basically, an old-style Clark-Y airfoil. Here's a plot of lift coefficient versus V over V0, this is velocity divided by the speed of sound, speed ratio. You don't see Mach number here. This is a report published in 1934. No Mach number, it's a speed ratio, but that is Mach number. And it showed what people knew, that as you increased in Mach number, subsonic Mach number, there is a critical Mach number beyond which the lift fell off the cliff. And he really measured very definitive data to show this. Lift coefficient. Here's the drag coefficient, showing it going out of sight. Moment coefficient, same kind of bad behavior. So these bad things were happening. They were measured very thoroughly, 1934, and still, what was really causing this to happen? It was flow separation, but what was causing the flow separation? Well, John Stack worked for Eastman Jacobs, who was well known throughout the United States, throughout the world, for the development of airfoil shapes. He was an NACA aerodynamicist at Langley, who had developed whole families of the famous NACA airfoils. Eastman Jacobs. Eastman Jacobs was a amateur astronomer, and he knew about optical systems. He suggested to Stack, why don't we put a Schlieren system across the wind tunnel, and let's see if we can literally see what is going on. Oh, at the same time, by the way, since there was this, people were perplexed, what is going on? Are we ever going to be able to make measurements in the speed range near Mach 1? Because here you have wind tunnels, but they're not very accurate in that speed range. There is no theory in this transonic aerodynamic range. There was no theory. The governing equations were nonlinear partial differential equations. And so there's sort of an unknown area. And Stack theorized that the only way we can really find out what is going on in this area is to build an airplane, an experimental airplane that would fly in that flight regime. And this is what he did. Actually, this is a piece of graph paper that I found in the John Stack files at the Langley archives a few years ago. It is a plot really of horsepower required. Horsepower required as a function of velocity, where he is taking into account, first of all, the compressibility effect, this big increase in drag, and not the compressibility effect. But the point is, he was thinking about an experimental airplane to probe this unknown flight regime. It did not go anywhere. He did publish this. By the way, you can find this, a more refined version of this, in the Journal of Aeronautical Sciences in the 1930s, but it's really interesting. As I said, I found this in the Stack files. It was sandwiched in between several IRS forms that he had filled out for previous years. So you have to look hard for some of this stuff. But he was thinking about this, and he was pushing for it, but it wasn't getting anywhere. Also, at the same time, airplanes were beginning to push higher velocities. And this is the Subaru NSX, the winner of the Schneider Cup Trophy, 1931, speed of 340 miles an hour for a closed circuit. And then 3 months later, the same airplane exceeded 408 miles per hour. And Stack and other people observed, hey, we're getting to the point where the whole airplane is going to become subject to these strange compressibility effects, not just the propeller. And so suddenly, these compressibility effects, and trying to explain them and figuring out what was happening, this intellectual endeavor to find out what is happening, took on a new light. The concern with what's going on in the tips of propellers, that was not a showstopper. But when you start talking about airplanes like this that you see on the screen, and airplanes flying near the speed of sound, then knowledge or lack of knowledge about these compressibility effects, they were a showstopper. And suddenly, this whole aspect of the compressibility problem became much more important in the middle 1930s. And still, the question was, what was happening? What was causing the flow to separate? What was going on? And this is where Eastman Jacobs, he was the boss of John Stack, and Jacobs suggested the use of a Schlieren system. And what I'm showing you here is the first time that shock waves were observed over an airfoil. This is 1934. It's in that high-speed tunnel that I showed you. And what you see here, this is a symmetric airfoil. Flow coming in from left to right. It's beyond the critical Mach number beyond which you get regions of supersonic flow over the surface of the airfoil. And what you see here is a shock wave. For the first time in the history of aerodynamics, the first time that a shock wave on an airfoil was observed. And suddenly, the intellectual knowledge of what was causing all these bad compressibility effects, lift going to pot, drag going out of sight, it was the existence, the generation of shock waves in the locally supersonic flow. Even though the flow out here is subsonic, the local pocket of supersonic flow here terminated by a shock wave. At the surface of the airfoil, the shock wave, big pressure increase across the shock wave, separated the boundary layer, and presto, this was the source of these adverse compressibility effects. That was the true engineering science knowledge for what was going on with these compressibility effects, bad effects on airfoils. It wasn't accepted by everybody. I'm going to read you something else, just one other thing here. This is a commentary on photographs like this. And by the way, the windows on the wind tunnel, they were pieces of celluloid. So that's why the quality of the photograph is not so good. But hey, it was pioneering. I'm going to read you here something that was written just at this time. The first tests were made on a circular cylinder, not the airfoil, but the first tests were made on a circular cylinder, about 1/2 inch in diameter. And the results were spectacular in spite of the poor quality of the optics. Shock waves and attendant flow separations were seen for the first time, starting at subsonic stream speeds of about 6/10 times the speed of sound. Again, not using the term Mach number, 6/10 the speed of sound. Visitors from all over the laboratory, this is the Langley Memorial Laboratory at Hampton, from engineer in charge, H.J.E. Reed, on down, came to view the phenomenon. Langley's ranking theorist, Theodore Theodorson, this guy, viewed the results skeptically, proclaiming that since the stream flow was subsonic, what appeared to be shock waves was an optical illusion, quote unquote, an optical illusion, an error in judgment, which he was never allowed to forget. So, you know, even the best aerodynamicists, the NACA aerodynamicists of the day, made an error in judgment. Well, this finally, the source of this compressibility effect was known, was discovered, an intellectual discovery. This intellectual knowledge was available before the design of the Bell X1. It was vital knowledge at the time of the design of the X1. Now, just a couple of other things, and then we're going to quit. The Lockheed P-38, designed by Kelly Johnson, top speed level flight over 405 miles an hour. In a power dive, it was much faster. And the P-38 was encountering problems in a power dive. It's called the tuck under problem. Here's the P-38 going down a dive. You normally pull out by deflecting the elevator back here on the tail. What happened is that all of a sudden, it started tucking under even more so on the vertical position and didn't pull out, couldn't pull out. It's called the tuck under problem. Ralph Verdon, who is one of Lockheed's best test pilots, was killed in the crash of a P-38 due to the tuck under problem. This became a big question. At the time that these crashes began to happen, there were hundreds of P-38s on the production line. And what to do? But here's what was happening. This is a bar chart showing for the P-38 in level flight, Mach number. Operational dive speed was beyond the critical Mach number, and in a terminal dive, well beyond the critical Mach number. And this is where that tuck under problem was happening. It was this is controversial, and it's a whole other presentation in a sense, but it was really the NACA aerodynamicist with John Stack who finally explained what was going on. P-38, seating well into the critical Mach number. The flow angle, essentially the lift decreased dramatically. The downwash behind the wing actually decreased. The tail saw a flow angle that was totally different than it was designed to see. It saw a much higher angle of attack, and the tail said, I'm going to produce lift. So the tail produces lift. P-38 goes this way. And this problem, by the way, was encountered not just by the P-38, but also by, for example, the P-39, the P-63 a little bit later on. But the thing is that Stack recognized that the lift was being decreased, the downwash angle behind the wing was being decreased, the tail was seeing the wrong angle of attack. How to fix it? The fix was through this intellectual knowledge. Stack realized they had to increase the lift on the wing. And this was done by adding little tiny flaps underneath the wing, about 30% of the chord line downstream of the leading edge, little wedge-like flaps about the size of my hand. And what those flaps did, when deployed, it locally increased the lift on the wing in this power dive, readjusted the downwash angle, flowing over the tail, and allowed the pilot to pull out of this tuck under problem. So that kind of intellectual knowledge was, in addition to helping later on to design the X1, was really pivotal in saving, in many respects, the P-38. So again, just an example of this intellectual knowledge and how important it was. Still, I show this graph because if you look at, I'm just generic plot, drag coefficient versus Mach number, and the subsonic range, we kind of know how to do things, calculations, you can make calculations, experiments were well behaved. Over on the supersonic side, same thing. Experiments were obtained, calculations were made, known, but the unknown still was this transonic gap in between, right around Mach 1, still a relatively unknown flight regime. And that is what prompted, finally, the Bell X1. And finally, I want to show you this from Collier's magazine. The Collier Trophy had been and still is today awarded every year for the most important development in aeronautics. The Collier Trophy in 1946 was awarded to these gentlemen, 1948, because the flight of the X-1 was 1947. It was awarded to these gentlemen: Chuck Yeager, the pilot of the airplane; Larry Bell, head of Bell Aircraft, the designer of the airplane; and John Stack, the aerodynamicist who made all this happen. And I want to point out something just incidentally. Notice here we have pilot, there we have manufacturer, here we have scientist. Scientist. John Stack was a dyed-in-the-wool aeronautical engineer. You know, this still happens today. Down at Cape Canaveral, down, you know, if there's a launch of a rocket, and everything works beautifully, the newspapers say, boy, the scientists have achieved it again. Success. The thing blows up, the engineers have made another mistake. Still happens today. But anyway, John Stack shared in the Collier Trophy for his work in the historic flight of the Bell X-1. And finally, he was awarded a second Collier Trophy in 1953 because finally the problem with wind tunnels was basically solved, also by Stack and his crew, by the design of what was called a slotted throat wind tunnel at Langley, which allowed transonic flow in the wind tunnel test section of such a nature to allow accurate, reasonable measurements at transonic speeds in the wind tunnel. So he received a second Collier Trophy. Just one little final aspect, since I've talked about John Stack. John Stack had, in 1958, when the NACA was absorbed into NASA, or NASA was created and sort of NACA morphed into NASA, John Stack went up to NASA headquarters in Washington, become director of aeronautics. After 3 years, he became totally disenchanted because within the newly formed NASA, the second A was being funded much more than the first A. Aeronautics funding was being basically ignored. So he retired, basically quit. He was retired. He became a vice president for engineering at Republic. And when Republic was absorbed into Fairchild, he became vice president of engineering there. In 1973, he retired. He retired to his farm down in Yorktown, Virginia. That summer, that July, while riding horseback on his farm, John Stack was killed. Stack is buried in a cemetery in Yorktown. And I have to think that every time an F-15 or an F-22 takes off from the Langley Air Force Base at Hampton, flight path is right over John Stack's grave in Yorktown. And I have to believe that John Stack is looking upward and smiling because of his role that would allow those airplanes to fly like they do today. And so that's the history, that's the story of the intellectual achievements of our understanding of what happens associated with flight near Mach 1, and that allowed the design of the X-1 and allows our supersonic flights, our supersonic airplanes today. So I'm finished, that's it.